Good morning everyone. Today, I am going to talk to you about the fascinating world of chemistry and the differences between metals and nonmetals. Today's presentation will explore how metals react with dilute acids to form salts and hydrogen, and how the varying reactivity of metals can be described in the reactivity series. We will also look at how metals and nonmetals react differently and explore the unique characteristics of each. So, fasten your seatbelts and join me in this exciting journey to learn more about chemistry. Metals are an important part of our lives. They are solid, with the exception of mercury, which is a liquid. Metals are generally hard, although lithium, potassium and sodium are softer. They have a shiny surface, known as metallic luster, and can be beaten into thin sheets and drawn into wires. Metals have high melting and boiling points, although gallium and cesium have much lower points and can even melt when held in the hand. They are good conductors of heat and electricity, with silver and copper being the best and lead and mercury being poor. Additionally, when beaten, metals produce sound. Today we are looking at nonmetals. Nonmetals may be solids, liquids or gases such as carbon, sulfur, phosphorus, bromine, oxygen, hydrogen, nitrogen and iodine. Nonmetals are soft, save for diamond, which is the hardest natural substance. Nonmetals lack luster, although iodine crystals do have luster. Nonmetals are not malleable or ductile and have low melting and boiling points. Nonmetals are poor conductors of heat and electricity, with the exception of graphite. Nonmetals also do not sound when struck. Metals and nonmetals react with oxygen in different ways. Metals combine with oxygen to form metal oxides. For example, when copper is heated, it combines with oxygen to form copper oxide. Similarly, when aluminium is heated, it combines with oxygen to create aluminium oxide. Some metal oxides are basic oxides as they react with water to form bases. While other metal oxides display both acidic and basic properties and are called amphoteric oxides. Examples of this include aluminium oxide and zinc oxide. Metals form a large part of materials used in everyday life, and their reactivity with oxygen is an important factor in how they are used and stored. For example, potassium and sodium react vigorously with oxygen and so must be stored in kerosene to prevent them from catching fire if left open. On heating, magnesium, iron and copper all demonstrate different reactions. Magnesium burning with a bright flame, iron glowing brightly and copper forming a black coating of copper oxide. However, silver and gold remain unreactive with oxygen even at high temperatures. In addition, some metals like magnesium, aluminium, zinc, lead and others form an oxide layer on the metal which protects further oxidation. These are called self-protecting metals. Metals like sodium and potassium are highly reactive with water, forming metal oxides and metal hydroxides in addition to hydrogen. When reacting with cold water, sodium and potassium cause violent reactions, resulting in the formation of sodium hydroxide and hydrogen and possibly even fires. In contrast, calcium shows a lesser degree of reaction by forming calcium hydroxide and hydrogen, while magnesium only reacts with hot water. Metals such as aluminium, iron and zinc react only with steam and form metal oxides and hydrogen. Lead, copper, silver and gold, however, show no reaction to water. Metals have a wide range of properties which makes them very useful in everyday applications. Their reactivity is an important property in chemistry and can be observed when metals are exposed to dilute acids. When magnesium, aluminum, zinc, and iron are combined with dilute acids, their reactivity is as follows. Magnesium reacts with two hydrogen chloride molecules to form magnesium chloride and hydrogen. Aluminum reacts with 6 hydrogen chloride molecules to form aluminum chloride and 3 molecules of hydrogen. Zinc reacts with 2 hydrogen chloride molecules to form zinc chloride and 1 molecule of hydrogen. Finally, iron reacts with 2 hydrogen chloride molecules to form iron chloride and 1 molecule of hydrogen. There is a predictable pattern of reactivity for these metals, with magnesium being the most reactive, followed by aluminum, then zinc and iron being the least reactive. Metals can undergo a displacement reaction, in which a more reactive metal takes the place of a less reactive metal in a salt solution. An example is when magnesium, zinc, or iron displaces copper from a copper sulfate solution. The reactions between the metals and their salts are usually completed within 15 to 20 minutes. Metals are essential elements in many products and processes in our modern world. While some metals are extremely reactive, others require a stronger catalyst in order to react. Understanding the reactivity of metals is very important in many industries such as construction and engineering. The reactivity of metals can be arranged in a decreasing order from most reactive to least reactive, known as the reactivity series. This includes potassium, sodium, calcium, magnesium, aluminium, zinc, iron, lead, and hydrogen. Knowing the reactivity of these metals is key to completing tasks efficiently and successfully. Metals lose electrons and become positively charged ions, while non-metals gain electrons and become negatively charged ions. Sodium, with an atomic number of 11 and an electronic configuration of 2, 8, 1, loses 1 electron to form a sodium ion, Na+. Chlorine, with an atomic number of 17 and an electronic configuration of 2, 8, 7, gains 1 electron to form a chloride ion, Cl. Understanding these properties of metals and nonmetals is essential in order to comprehend the periodic table and chemistry. In this slide, we are looking at elements in the chemical world, specifically metals and nonmetals. We will take specific examples of sodium and chlorine, which have an atomic number of 11 and 17 respectively. Sodium has an electronic configuration of 2, 8, 1 and a valence of 1 electron. To form a sodium ion, it will lose 1 electron. Chlorine, on the other hand, has an electronic configuration of 2, 8, 7 and a valence of 7 electrons. To form a chlorine ion, it will gain 1 electron. Finally, due to the attraction between the sodium and chlorine ions, a sodium chloride molecule is formed, sodium chloride. The slide titled, Chemistry Metals and Nonmetals, focuses on the formation of ions in magnesium and chlorine. Magnesium has 2 electrons in its outer shell, so it needs 2 more electrons to become stable and, thus, forms 2 megagrams 2+ ions. In the same way, chlorine has 7 electrons in its outer shell and needs only 1 electron to become stable, resulting in 1 Cl ion. A table on the slide displays the atomic number, electronic configuration and the ions formed. Ionic compounds are formed from a combination of a metal and a non-metal element, where electrons move from the metal to the non-metal. As a result, these compounds are solid crystals with high melting and boiling points, and can become electrical conductors when in molten state or in a solution. Although they are soluble in water, they are insoluble in organic solvents such as petrol and kerosene. Metals have a wide range of uses, from construction to energy production. Their reactivity levels, however, can vary greatly. To ensure the best metal is used for the right application, it is important to understand their properties of reactivity. This presentation will delve into the different methods employed to process ores and create pure metals of various reactivity levels. These methods include electrolysis of molten ore, carbonate ore, sulfide ore, as well as calcination and roasting of oxide metal ore. It is impressive to consider the intricacies required to bring pure metals from raw ore. Metals which are low in the activity series can be reduced to the metal by heating in the presence of oxygen. A good example of this is how mercury is obtained from its ore cinnabar, through a process of heating in the presence of oxygen. First, the cinnabar is converted into mercuric oxide, and on further heating, it is reduced to pure mercury. Similarly, copper is obtained from its sulfide ore by heating in the presence of oxygen. This process of roasting metals is an essential step in the extraction of metals from their ore. Metals like zinc, iron, and lead may be found in nature in the form of oxide, sulfide, and carbonate ores. It is easier to extract metals from oxides, thus non-oxide ores are converted to oxides via a process called roasting or calcination. Roasting involves heating an ore in the presence of oxygen, while calcination involves heating an ore without oxygen. The oxide ore is then reduced to metal by heating it with a reducing agent, typically coke or carbon. This process produces the metals used in our daily life. Metals and non-metals are integral to our lives. Metals possess properties such as malleability, electrical conductivity, thermal conductivity and reflectivity, making them suitable for industrial and commercial use. Non-metals, on the other hand, have characteristics of low conductivity and insolubility in water, making them fit for functions like insulation and packaging. This presentation provides a brief overview of these two main elements and their respective characteristics. Metals such as potassium, sodium, calcium and aluminium are reactive and cannot be extracted from their ores simply through heating or heating with reducing agents. To acquire such metals, they must be attained through the electrolytic reduction process of their molten chlorides. For instance, when electricity is passed through molten sodium chloride, sodium metal will be deposited at the cathode and chlorine gas is produced at the anode. Refining of metals is a necessary process to obtain a pure form of metal from its impure state. Electrolytic refining is the most common method used for this. It involves making a block of impure metal the anode and a thin sheet of pure metal the cathode. The electrolyte used is a salt solution of the metal to be purified. For example, when refining copper, the electrolyte is an acidified copper sulfate solution. When an electric current is passed through the electrolyte, the pure copper from the anode is deposited at the cathode. Meanwhile, the impurities settle down as anode mud. Corrosion is a natural process that causes destruction of metals due to reaction with oxygen, moisture, carbon dioxide and other elements. Rust on iron is a prime example of this phenomenon, as is the green coating of basic copper carbonate on copper and black coating of silver sulfide on silver. To prove the necessity of air and moisture to cause rusting of iron, an experiment involving 3 test tubes with an iron nail in each can be performed. The first tube will have anhydrous calcium chloride, the second boiled distilled water and the third will just have water. After sealing the test tubes and leaving them untouched for a few days, it can be observed that the nail in the first tube will not get rusted, as there is no water present. The nail in the second tube will similarly remain unrusted, as oil has been used to seal it and hence not allow air to enter. However, the nail in the third tube will have rusted, as the only element inside is water. Metal corrosion can be prevented through a variety of methods, each of which has its advantages and disadvantages. We can apply oil or grease to the metal, paint or galvanize it with zinc, tin it, electroplate it with a less reactive metal like chromium, or alloy it. An alloy is a mix of a metal and other metals or non-metals, like steel, which is a mix of iron and carbon, or brass, which is a mix of copper and zinc, or bronze, which is a mix of copper and tin, or solder, which is a mix of lead and tin. If one of the metals in an alloy is mercury, it is called an amalgam. I hope this overview of corrosion prevention has been informative, and thank you for your time.